Okay, looking at your packet on 13.3, there's a note on, I guess it's number 13. So it says in the last integral, you could conclude from the integral around the whole path, from the integral you did for the two piecewise paths, you could conclude the integral for any third path. And I just kind of indicated that, so it's no surprise there. Okay, on number 18, using the fundamental theorem for path integrals, I got something a little different than what you got. I got like 1 minus 1 over e, you got 2 minus 1 over e. I don't say anything wrong with what I did, I don't say anything wrong with what you did. See if you can find it. Some of the pages I'm having a little trouble reading at the top. And number 19 I didn't really get to do a good review on. I couldn't read what the problem was. But everything looked good, so I think you're all right. Question on number 25. Why does zero curl imply path independence? What's the geometric connection? Of course, it's very easy to prove it just using symbols. But I'll just point out, in terms of the diagram I happen to have here from yesterday, that here's an example of a function with non-zero curl, you'd call the situation here. So we have vectors of constant magnitude around this circle, vectors of constant magnitude around this circle, and these vectors have greater magnitude than these. Well, if I do a path, just take two radial lines, and I do a path from here to here, around here, here, and back. Clearly, the integral along this path and this path, the integrals along these two paths are zero, because along each radial path there is no radial component to the vector. Now that's not necessarily true for any vector field, but if it doesn't have, if the curl is non-zero, you're going to have at least some component of it acting like this. Okay, so that you have zero along this path, zero along this path. Along this path, the path is both longer and the magnitude of the vector field is greater along this path than along this path. Which means, of course, that the integral around the closed path is going to be non-zero, and that means that the integral from, you just choose any point, but I'll just choose the integral from here to here along this path is not equal to the integral from here to here along this path, because this integral is equal and opposite to this integral, and this integral is not equal to the integral along this path. Okay, and if you have a radial field, I'll just draw that much of it for time. Okay, a radial field, the magnitudes of the vectors don't always have to be the same. You can consider a similar integral, and these are along arcs of circles concentric with the what do you call that, the pole filled with a radial field. And if you consider this, okay, I'm assuming, I said a radial field, a radial constant field. And actually, not even a radial constant field. It's a radial inverse square field, it's going to work. So, if you consider such a path, you get an idea why a field that's conservative has to give you a path independence, has to give you zero path around here. I don't want to go too much further into that, partly because I'm not sure what I want to say there next and how much I'm going to say. Okay. And duly noted that you went and solved a differential equation at number 30. No surprise that you solved it. I'm thinking that you're maybe overusing the 3 dots for therefore. I would think that usually you would want to use the 3 dots when you're drawing the final conclusion from some line of reasoning, rather than places where you could use, okay, let's assume this, then this happens, then this happens, and this happens, therefore this happens. You probably don't want to say, well, assume this, therefore this, therefore this, therefore this, although it's not not grammatically incorrect. I think it's a little bit of an overuse of the therefore. And take that for what it's worth. Other people that know more than I do might well disagree. Anybody that lives even less than what I do, who, probably don't want to listen to them. Okay. What in the world? Well, that's a del. Okay. Can't read my own note. On number 36, you do a good line integral and so forth to show something that you could have shown very easily in about one step using the fundamental theorem for path integrals. Okay? Because the field is very clearly conservative, you could have just used the endpoints. Now, I'm not sure. I didn't read the instructions for the problems. The instructions, I said, actually do all those integrals. But I kept having the feeling that you were doing a lot of integrals that you didn't really need to be doing if you're going to use the path independence, which is one of the big ideas in the section. Okay, so number 43, same thing. You end up having to solve g prime of x equals negative 5g of x over x, or x g prime of x equals negative 5g of x. Either way, but going through the curl and setting it equal to 0 and so forth takes a lot more steps and a lot more possibility of error than simply using the fact that the y derivative of the x component and the x derivative of the y component have to be equal. Okay, you really messed up on number 45. You're showing something about the gravitational field, and you're trying to show, what are you trying to show there? Because what you got, just you move from point A1, B1, C1 to point A2, B2, C2, and you find the work done on that path. and you didn't get the right answer, which I know very well from physics what the right answer is. So when I looked at it, I wondered what was going on. It took me a while to figure out that your small r is the magnitude of your big R, but you've got the small r outside the integral. And you really can't do that. And you see exactly. So go ahead and fix that one. I didn't understand a dream I had last night until I got to number 49 and saw your picture of Al in a motorboat. If you think of Al in a motorboat, there's something important that you don't know about Al. I'll comment on that in a separate video because I can kind of quote what he said in the dream. Okay, so and for anybody who picks up on this, that's an inside joke. Okay. Yeah, okay. On number 49, I've got a note down there that even I can't read because I didn't write my U very well. I just say, you say that this vector field F equals negative A, negative B, A and B constants, is conservative because the curl equals 0. Well, even more simply, it's 0 because your Uy equals your Vx, which is 0. In other words, it's a constant field. Nothing wrong with your solution. Just pointing out there's a simpler way to have established that. Okay? And it's the U and the Uy that I couldn't read, so I thought I'd better draw your attention to that. Okay, show the vector field is conservative, then dp partial p with respect to y. Okay, and basically all you're showing is that the coefficients of I, j, and k in the curl, expression for the curl, are all equal to 0 if the field is conservative. And that's great. I'm just wondering if you could think of a direct proof of that without using the curl, or proof based on geometric interpretation. That'd be a geometric interpretation in 3 dimensions, and I haven't even thought about what that would look like, but I've got an idea how I would start. So just an idea I'm tossing out there. Okay. Work done in a central force field is given by 1 over R1 minus 1 over R2, which is the result I think you should have gotten on number 43. And you got it. Everything looks good on that one. You used the fundamental theorem for path integrals, conservative fields, and everything looks really good there. Okay. I want to look a little more closely at the book statement in number 55 to see what they have done on the proof of theorem 13.5 before I comment any further on your last proof. But everything I see looks pretty good, and think of how it's related to some of the things, extraneous things that I've done in a proof of Green's theorem. Okay, very good.